Hello, Professor. My name is Mohammed Mansour, and this is my final project presentation for the Robotics and AI class. My project is going to be about implementation of a model-free based mobile fire extinguishing agent in a dynamic environment, which means a self-autonomous driving robot that is able to navigate a layout, navigate an environment, searching for a fire while avoiding an obstacle. So I'm going to use reinforcement learning, the off-policy Q-learning algorithm, in order to make the robot first learn about the environment and construct its Q table, and then it is going to be able, hopefully, to navigate um, through the environment in a an effective way, avoiding obstacles and reaching the fire position at the fire location at the same time. So the Q-learning algorithm is quite simple. Um, it is going to be is this manner. We're going to initialize a Q table arbitrarily and repeat for the number of specified episodes while initializing a state for the robot. Repeat for repeat the step of the episode, and every time we choose an action from a state space, we're gonna create a policy, either a greedy policy or taking an action that can get the maximum reward through a specific discount rate and learning rate, plus the reward associated is going to be converted to the new Q value. This is also the Q value, the Q learning algorithm um, formula in a more sophisticated way. So this is the old value here. We got the pair, and these are the pair of state action we need to update. We're gonna multiply it by 1 minus the learning rate plus the learning rate itself multiplied by the reward plus the discount factor multiplied by the maximum action taken by uh, the Q state, which is the estimate of the optimal future value, which is the uh, the the action that can get me the maximum Q value for the next states. So it's actually an easy implementation. It can be done in a software in a software way. So here we have we can open folder. Yes. So here we have our implementation as well here. So for the first time we have the either the Q table. We're gonna have our Q table, and we're gonna use it for testing, or we can specify none for the training. So in this case here, we are going to show how it is performed in the training, in the testing. So we're gonna take a size of 5. We're gonna make a small iteration just to see how it is performing. And there is like some cost associated with movement and with failure, and a big reward with extinguishing. We can also have a high epsilon, which is indicates the dependence on the Q table versus exploration. So high epsilon means more dependence on exploration, and low epsilon means dependence on the Q table, which is exploitation. So in the testing, we're going to exploit. We're going to exploit our previous knowledge and our previous training knowledge about it. So this is it. We're going to create our layout, and we're gonna color the robot is blue, the dynamic obstacles and the static obstacles with green, and the fire with red. And now we're gonna create a class for the blobs, It's going to have two main functions, the action functions, which specifying eight actions, either up, down, and left, right, or diagonally movement as well. And the movement function, which is ensure that the movement is within the boundaries and every action gonna lead to its specific movement. Then, in case if it's none, which means that we are in the training mode, it is going to arbitrarily create a Q value table. Otherwise, it is going to load our previously saved Q table. So here we are going also to specify that robot to take a movement, an action, a movement based on an action, and we're gonna move a dynamic obstacle arbitrarily. The fire and the static obstacles are going to be stable. While we are going to create a sleep time, so in order to visualize it better. So here we are assigning the exploration versus exploitation based on our epsilon value. We're gonna, if it's high, so we're gonna depend more on the Q table. Otherwise, we are gonna take a random action. So here the robot is creating its own belief, and its own belief is based on the displacement between the robot and the fire, and the displacement between the robot and dynamic obstacle and the static obstacle. Based on that, it is going to create its own coordinate system. So in case it took an action that led to hitting a dynamic obstacle or static obstacle, it's gonna associate it with the failure cost. If it reaches the fire, it's gonna release extinguishing reward. Otherwise, while still moving, it's gonna get a movement cost. And this is going to create our current reward. So we also going to need our new observation. And our new observation, we're gonna look at it in our Q table to see what's a maximum future Q based on that Q table values. And we're gonna retrieve our current view so we can implement our Q table algorithm as here. 1 minus the learning rate times the current Q pair plus the learning rate times the reward plus discount times the maximum future Q. And this new Q is going to be our old Q in the next iteration. And so forth until we finish our episodes and thus creating our final Q table. And now here we're going to show our success ratio as the successful attempts over all the total attempts. Now we are ready to run our code and see how it will perform. Here, this is I trained this agent for 11 hours and used the Q table saved to um, to show the actual robot movement. So let's see. Okay, I need to put the file pickle. Pickle, I guess now is it. Now when we run, we will see. Yeah, this is the robot in blue, and it is trying to avoid the obstacle and reaching the fire at the same time. See, so it's trying to avoid the obstacle and reach the fire in the same time. So it is quite smart now. See, it is waiting for the obstacle to be away and getting to it. Yes. So it is quite smart now. Keep in mind, I trained it for just 11 hours. Sometimes training it for over than that using more powerful machines can enable more successful attempts. So here we have 80% success ratio. Whoa, it's really good success ratio. And this is my implementation for that. And I hope I hope this presentation is quite meaningful, and it showed every aspect of my final project. Thank you, Professor, and thank you for the good semester. Goodbye.